Swayam Prabha. Digital India. Educated India.
So in the last class, we were talking about the particle under equilibrium, and then we tried to extrapolate it to a rigid body. And then we said that a particle if it is under equilibrium, so if this particle is under equilibrium, then that implies sigma fi is 0. So similarly, sigma fi being 0 also indicates that the particle is under equilibrium. And then we try to extend it for a body here. And then we said that it's made of a number of particles. And if the body is in equilibrium, this is what we said, right? Then it implies every particle is under equilibrium. And that implies that sigma alpha is 0. Okay, it's one way. Okay, if this is in equilibrium, sigma alpha is 0. And the reverse is true for rigid body. This is what we said. This is still incomplete. I'm going to make it more complete just now. Our discussion is still not complete. This is only partial. So this we showed for taking one-dimensional two particles and so on. So we said that sigma fi is 0 implies that the two particles making each particle will be under equilibrium only in the case of rigid body. So this is what we said last time. In fact, this is still not complete for many things. Sigma fi being 0 as a vector means that it is 3 scalar equations. So that is still not enough. Okay. This is because let's talk from another point of view. So what I was saying is that we are more concerned with bodies. So, and then if the body is under equilibrium, then it definitely implies that sigma fi is 0. But the reverse is not really true. It's only true for rigid bodies, which means that if sigma fi is 0, then each particle will be under equilibrium, meaning that the rigid body will be under equilibrium. So this is still not complete. I showed it only for 1D, but coming to 2D, we have some other, what do we call as the degrees of freedom. So which we have to take into consideration also. So what I mean by degrees of freedom. So degrees of freedom is that consider that there's a rigid body here, and if it is moving in 2 dimensions, so it can go like this one. So in motion, so it can go like this one. So which means that it has translation, 2 translations, as well as a rotation. So a body, a planar body in 2-dimensional motion has 3 degrees of freedom. So I still have to talk about that. What is that which we need to understand? One is, of course, this has come even before Newton. We have Galileo, who worked on these static equilibriums extensively. So he enunciated that sigma fi is 0, as well as there is one more equation. He also said that sigma of moment of all the forces about a point, any point, ma is 0. Okay, sigma all the forces, moments of all the forces taken about some point here, say maybe point A. So if you take all the forces, and that should add up to 0. So that's what he said. Obviously, it is true. And this is for static equilibrium. On the other hand, let's also look at from another angle. I'll bring in the equations of dynamics, which I will prove later. So let's which will be what I mean is that if you have on a rigid body, so this will lead to a translation and rotation. So if you talk about 2 dimensions, so this will lead to, say, there is one significant point known as G. G is the center of mass. So this will result in sigma Fi is mass times Ag. Okay. And sigma M of all the forces about G is Ig times alpha. So these are 2 equations which we will prove it a little later, but I want to argue the static equilibrium from the point of a complete degrees of freedom in dynamics. Okay. Dynamics, which we will prove later. So for the moment, you take it that all the forces will be equal to this vector equation. So this will lead to the acceleration of the center of mass. So, and there is also another equation. The moment of all the forces about G will lead to a Ig times alpha. Alpha is angular acceleration. So that means that so if you have the body is under motion like this one, so obviously G here has moved to, which we would call as a translation X and Y, and together with that, so we also have a certain rotation, right? So thus we know that the same thing will be true here. So the translation part, the acceleration of the translation is governed by some of the forces, and the rotation is given the moment of the forces. So here the G is the most important point here. Moment about G is Ig times alpha. This is again, this is part is for the, now the first part is good for the any 3D. The second part, writing it as Ig times alpha, is only true for 2D. Okay. Actually, when we go to the 3 dimensions, we have to say the rate of angular momentum. Okay. So we'll do that later. But mainly we concentrate in 2D. So essentially what it is that, so looking at the dynamics of the body, then we come to the statics. So that is another thing. Galileo has already said that the equations will be alpha is 0 and is 0. So from this point of view, if this is under equilibrium, so if under these dynamic equations, if you want to apply to static case. So if you do that, then what happens is that the body is under equilibrium, which means that AG, every point in the body, particularly the G, is having zero acceleration, as well as alpha is also having zero angular acceleration. So if this is so, then what we have here is obviously the sum of the forces, okay, will be added to zero, and similarly mg is zero. Okay, so this is what we get from the complete dynamic equation. So from this can we derive some more equations which are convenient for us as well as more powerful? So what we mean by this is that, so for static equilibrium, we said that the sum of the forces should be zero and the moment about G should be zero. Okay. So on a rigid body, so for static equilibrium, so this is what's going to be. This is what's going to be, right? And so from this one, mg being zero, so we can also derive slightly a different. Is it also equivalent to A being any point? So from dynamics, so if G, this is what this says about G is zero. So what about if I take another point A here, anywhere else? So is it also imply that MA is zero? Okay, so these are some of the basic questions, philosophical questions, which you need to answer. You know it, but I want to be clear in your mind that can we show, if these two are given, can we show is MA is also zero about? Okay, so how do we prove that? So say Fi being zero, so let's just say that Fi, so that means let it be equal to some R, and if that's what, and that means that the whole of this thing can be shown to be some R, say mg here. So this is at G. So this is at G. So this is what's good, right? So this is equal to R, okay? And so you know that sigma Fi is MA, which is equal to Fi is R, and so that can be shown here. And so everything is, so in fact here, if you go back, either you do it like this or do it like this, fine. So similarly here, mg is I alpha. So you see that that is going to give you a thing, and the moment of R about G is zero, which is leaving out only the mg, which should be equal to Ig times alpha. So this you would have understood. Okay, so if this is the case, now how can we say that if R is zero, and mg is zero, obviously, what about any point A here? In fact, there's one thing which you would know is that how do you transfer a force to another point? Say, for example, if you have a here at point, there's some P here, which is being shown here. The one thing is that you would have realized that if it is acting at P, the force can be translated, right? Okay, to any point on. So the effect of this force on this body, say either here or here or here. Okay, so this is a translational thing which you can do. Okay, and on the other hand, okay, so what about, you would have realized now, what about M? How is M created? M is created because M is a couple is created by two forces which are equal and opposite and acting at a distance away from this. So you know that if the distance d is here, so you know that the moment is F into d, and so this is which can be represented simply a M shift like this one. So either you apply two forces like this one or completely remove it and then you put it M as here. So where is it? This is very important for you while doing all the problems. Is M acting here, or shall I put it here, or shall I put it here, or shall I put it here? Where do I put? Where do I show that M is acting? The sum of the forces is 0, but however leaving out a couple, a moment. So where is it acting here? So can you tell me where it is acting? Is it acting at G? Is it acting at A or B or anywhere? So in fact, you can show it if it is a pure moment. So you can show the moment is acting anywhere. It doesn't matter as far as the rigid body is concerned. So it doesn't really matter whether you show it here or show it here, show it here, as long as it is in the body. Okay. So this is how, in fact, vectorially you can also show that if you have another point O here, moment also can be shown to be as R cross F. And maybe F1. And if you have a number of them, you can do that. Okay, of course, from this also, you can, a moment, how is R1? This is F1, F2. If this is R1, if this is R2, you know how to take the cross product. And this is the moment due to F1, this is the moment due to F2. And if F1 and F2 are equal and opposite, so it is simply R1 minus R2 times F. So that is nothing but, wise, it is the distance multiplied by the force. So you know that much, right? So, yeah.
So, like, there's a catch over here, right? Like, the forces that are being applied to a body are constant, no matter where they're applied. If it is F1 in magnitude, it will be F1, but the moment can vary depending on the point that we choose to calculate it.
You are not talking about the motion, right? So as long as
only the moment, like the moment will vary depending on the point that we take, isn't it?
No, along the same straight line, with the force being moved won't make a difference, right?
Right. Yeah. So if you have an F here, so either you can ensure that it is here or anywhere here. So it doesn't matter. So similarly, this is for F. This is equal and opposite. So it can be anywhere here. So what it is that maybe if you want me to expand this one, so if you have, say, some point O here, and so this is A and this is B, and this is the position vectors. So the if you want to find out the moment about O, which will be okay, moment about O, if you want it, so it is nothing but R1 cross F1 plus R2 cross F2, right? So essentially, F2 is the same as with negative sign. So it will be R1 minus R2 times, say, let us say F1 only. So what is R1 minus R2? So R1 minus R2, if this is R1 and if this is R2, so this is R1 minus R2, right? So if I take a cross product of R1 minus 2 with F1, So what is it? It has a magnitude and direction. So it is nothing but, what is the word? It is nothing but the magnitude of F, magnitude of R1 multiplied by sine of this angle. So the sine of that angle, so R1 minus R2 with the sine of that angle. So if you see that, it is nothing but the distance. Okay, so this is nothing but the distance d times F1. You understand? So that is the cross product, right? So here, so it doesn't really matter now. It is only, finally we boil down the distance between these two forces. So whether it is acting at A, okay, or maybe a little bit here. So R1 minus R2 cross is nothing but the distance between the forces, right? So that's what you are asking, right? Is F1 acting here or here or here? Will it make a difference as far as this
No,
is?
like my question was like whether we take O or O prime or any other point, the moment will be same df1, right?
Exactly. The moment will be same, right?
But this is only the case when f1 and f2 are equal and opposite to each other.
Exactly.
Like,
That's true. That's true. I'm limiting my discussion to F1 and F2 being equal and opposite in direction. So this is going to create a pure couple. That's all what I'm saying. I'm saying how is the, because you keep getting this moment and a couple and all that. So I just want to make sure, make you to understand that what I was asking is that where is this moment acting? So say if you have here, there are forces and these two are now replaced by, say, you think that the moment acting here, which is of this magnitude, or acting here, because I could have taken the O anywhere, right? I could have taken O anywhere. I could have taken O here, or maybe a O prime or O double prime. So always it is the same. So what does that mean? It means that as far as the effect of this couple of forces is concerned, so it doesn't matter whether you consider it here or here or here. Just like this force here, just like whatever I was talking about this force, whether you assume that it is acting here or here or here, it doesn't matter as long as its effect on the body. Okay, let me also tell you on the rigid body. Okay, if you talk about deformable bodies and if you want to find out what is its effect inside, okay, so that is different. That's altogether different. As far as the rigid body is concerned, it doesn't matter whether wherever the force is, as long as it is on the same line. So similarly, once you find the effect of this couple to be a moment, so it doesn't matter. You can assume that it is anywhere here. Okay, so please keep this in mind. Okay, yeah. So what we were talking is that, so if sigma f, which may be equal to r, if it is 0 and mg is 0, so does it mean, does it imply that the g here, which we took it to be 0, so that ma is 0, a being anywhere? Okay, so can you answer me that question? Does it mean that from this relationship, Fi r being 0 here and mg being 0, if it is given for static equilibrium, does it mean that if I take, say, if I have a g here and then here, okay, so if I take any other point, will it be 0? So how do we argue it? Okay, the arguing is that once you should also know very simple arguments, very, very simple arguments, but you should be clear in mind that how we are proceeding. So for example, I have a force here, let's say, and then I want to translate this force to this. What is that equivalent to? We say that. So can I translate to say it is some point A? I want to, because it has the same effect wherever it is. But if I shift it to C, if I shift it to C here, so is it going to have the same effect? So what we need to do is that F, if you want to shift this point, so it's essentially what? It's essentially that you're putting an and opposite F here, right? You understand? So I'm putting two forces which are equal and opposite, but at C. So what is the effect of these two forces? Effect of this F and this F, which are equal and opposite, is just equivalent to a couple, a moment, right? So that, and then so these two are replaced by a moment, while this is stays. So it means that the effect of F acting at A can be replaced by a same force and parallelly at point B and together with a moment. Okay. And what is this moment? So this moment here is what? D times F. What is D? So D is the distance between the perpendicular distance between the line of action to C. Okay. So these two are now equal. So you should know these things, because what are the equal things? So you can always transfer a force from a certain location to another location parallelly by taking that force as it is together with a moment which is equal to a D times F. Okay. So these are all, but at the same time, I'm just trying to recall all those things.
So does that mean that, like, if we have a rod at rest and if one person applies the force on one end and perpendicular to it, and another person after that applies the same force on the other end, then are those both scenarios equivalent to each other?
Yeah, that's what I'm saying. Say if I have what you're saying, that if I have a force here, and so then what can I do? I mean, this guy here, and there's another guy you want to have a B here. So what is this two equivalent to? So the two, I want to transfer A here. So if I want to transfer A to B, so that means that I have an F here. And what else? What else? So this is translated here together with a moment. So what is this moment? Of course, if you have a distance D here. So this is F. So these two are equivalent. So a person who is applying a force here at A and another person applying a force F at B together with a moment. So this is important. Don't leave out this force. I mean this moment. So these two put together is equal to this. You understand? Either you can do this or do this. Both are absolutely equal. Okay. But this translation, again, I caution you, is only true as far as these equilibrium considerations are concerned. It doesn't apply. Absolutely, you should not do that. If I want to, stress and strains, right? What are the internal forces? For example, at some cross section here, if I want to know what are the internal forces which will cause the tensile stress or maybe a bending stress and so on. So the kind of stresses which you create here inside and kind of stresses which you create inside here at the same location, in these two systems, it is totally different. Okay. But however, as far as our discussion of equilibrium is concerned, so these two are equivalent for a rigid body. Rigid body doesn't have any stresses. Okay. Rigid body doesn't have any stresses. So these two are equivalent. Do you follow it? I mean, this is what you are asking, right? If there is a guy here, another guy here, so if I apply the same force, but he should also bring in the moment. Okay, then those two are equivalent.
Okay, sir.
Yeah, you got it?
Yes.
Yeah. Okay, good. Yeah, we'll have more of this discussion as we go on. When you come and sit in the class, I'll be very happy. I can see you. Okay, all right. So I still have not completed this discussion. Yeah, what we were saying is that so what we are saying here is that the total force here, a number of forces, and so which is resultant is 0, and the and its moment about G here is 0. Okay, so what does that mean? So does it mean that it is also equivalent to, is this also equivalent to saying that MA is 0? Okay, essentially this is the two systems are sigma F is 0, Mg is 0. So is this perfectly equivalent to sigma F being 0 and M about any other point 0? These are. So is these two statements equivalent? You think so? Are they equal? So whether, which I derived this from the dynamics, whereas this which Galileo gave is obviously true too, and it is true. So do you think they are equivalent? Will one imply the other or not? Because that's very important for us, because I have a follow-up question, a follow-up thing here. Okay, let's look at this way. I mean, from the derivation point of view. So if, what does it mean by the G being 0, or for that matter, any, say I have a lot of forces here and I have a point 0 G here. So what does that mean? So if I say that M G is 0, can I reduce this? Can I reduce these three forces to a single force? It's possible, right? I have these three forces. I can bring it here with a moment. I can bring this here with a moment. I can bring this to a moment like this one. So there is a resultant together with a moment. Right? Understand? So if I bring all these three to the point G here, so this is what it looks like. I have an R here. R is the sum of and, which I'm going to put here, and together with a moment. So if I say mg is 0, what does that mean? Can we mg is 0 means that this is 0 as well as the r also is passing through 0, the same point G, right? Then only it becomes 0. Okay. So if I do any other point A here, so I can the same thing I can translate to A, and then I can, so if everything is 0 here, R is 0, Mg is 0, so obviously at A also it is 0. So R we can, so if I have an Ma 0 here and R being 0 here, so if I show it, so obviously the whole system anywhere is also, you follow it? Okay. So this is important thing for us. Either you write it here originally from dynamics, or write it like this one about any point, both are equal. Okay. So now let's look at another thing, interesting thing, is that these are three equivalent scalar equations. So in fact, this F is two equal. And it need not be just the X, it can even be X prime also. You can choose. So what it means that, so that means that every force here, instead of xy, taking xy component is 0, or you can also say x prime and y prime. You can take the components along x prime direction and y prime direction, so they also will be 0. So both are equivalent. So in fact, these directions are arbitrary. It can be x prime, it can be x double prime, and so on, right? So then I'll give equivalent statement. So you please, I'll write both of them. I'll write the scalar equations. So these are, in any system of forces, you will get 3 scalar equations if the body is under equilibrium. So I'll ask this question. So instead of that, x prime being 0, ma 0, mb 0, or 3 points. So because you keep getting n number of equations, so you can make this set of equations, or this set of equations, or this set of equations. Are they equivalent? That's the question. Are they equivalent? This is what we started off saying, that we add up to 0. This in A has to be 0. So here, what am I saying here? Instead of course, this is xy. What I'm saying is that this is x prime. So that means that you take the forces all in the direction of x prime and 0, and I take 2 points, the moment about all the forces about A, add up all these things to about A0, all the moments about B0, and so that will give you 2 equations. And in the third case here, the same set of forces, instead of taking the sum of the forces being 0, here I'm taking ma0 and mc0. So are they equivalent? And if they are equivalent, under what circumstances? Okay. So what does this mean? So this means that so that means that all the forces in the x prime direction added up should be 0. So what does that mean? So if I take some point here, say some point here, so that means that in the x prime direction, they are all added up to 0. So this force. So what does that mean? How is the resultant? So the resultant will be only in this direction. The resultant is in this fy prime. So this is the one which is there. So if you say fx prime, sigma fx prime is 0. So that means that the probability is that all the components may have some non-zero fy prime. So if ma is 0, so if I'm translating everything to A, so that means that there is no ma. So essentially the system is then, the system is only this, right? The system is only this, because there is no x component, x prime component 0, and there is no moment about A and 0. So what about, how do we interpret that MB is 0? In what way is it going to put a condition on fy prime 0? So what way the point B will be? B can be anything, or is there any restriction on B? So I took A arbitrarily, fine enough. Is there any restriction on B? If I take a B on this line, for example, on y prime line, y prime times the moment about this point will be 0 all the time, right? Because it's passing through this. So that means that this B, to be a valid third equation, to make fy prime 0, then B should not be on this line. B should be anywhere outside. So if it is here, obviously if Fi prime is going to be having a zero moment about B, so obviously Fi prime has to be 0, right? So thus this is a valid equation, okay, with a rider that B does not lie on Y prime drawn at A. So these three are also equivalent to this one, as long as you make sure that B does not lie on Y prime, right? So now this another set of three equations here. Here we are not talking about any F as such. We are talking about directly MA, MB, and MC. Okay. So if are there any restrictions on ABC? Are there any restrictions on ABC, or they can be arbitrary? So again, the same kind of arguments will go there. So if I say that the first equation, MA is 0, so what does that mean? How is the resultant? One thing is that there is no moment here. That first equation says that MA is 0. No moment. But how can there be a resultant here? So that means that the resultant is this. Resultant is passing through without a moment. There is no moment, because everything, whenever you translate, you end up with a moment, right? So in this says that there is no moment here. It is a pure R. So what does this B mean? So B, anywhere here, look at this second one. If you say B is also 0, MB is also 0, what does that mean? Where is the resultant? What is the restriction on the resultant? If it resultant passes B, then the resultant will not have any moment about B. But it is still there. It is going along the line of AB. So if it is just going along the line of AB, these two are satisfied. So how can we make sure that it is absolutely 0? So how do you make it absolutely 0? You have to take another point here, which is away from the line. Okay? If C should not lie on AB line. If C lies on AB line, so it doesn't exclude the possibility of the force going along AB. So if you want to exclude the force going along AB, then she should lie outside the line AB. So here C should lie outside AB. So in a nutshell, what do you call that ABC line, ABC points? If
non-collinear.
Non-collinear.
Yeah, exactly. That's good. Thank you. That's very nice. You are smart. So ABC should be non-collinear. That's all. So this is the restriction. So that means that either you use this or use this with a rider on B, or use this setup MA, MB, MC with a rider that ABC are non-collinear, then you can make sure. So what does that mean? So that means that this is equivalent to body, rigid body is under equilibrium. So all these four are equivalent. All these four are equivalent. Either equality is body with a number of forces is either under equilibrium, or moments about points ABC which are non-collinear 0, or x prime, fx prime is 0, but 2 points which are not on prime line, and then either you use this, so they're all equivalent. Okay, so this is yeah.
Sir, if they were collinear, then we wouldn't be able to establish the equilibrium condition, isn't it?
Yeah, if they are collinear, say for example, this, okay, we said that resultant. So if you say MB is 0, so which means that the resultant cannot be any, maybe like this, which is passing. So these two conditions say that the resultant may be passing along this AB. But if you want to make it absolutely 0 or also to be 0, so then point on this line, MC will be 0 as long as the resultant passes through AB. But however, if you want to make it to be 0, so C should be outside the line AB. So that's what we are saying. That's what also your friend has said, that ABC should be non-collinear as long as they are not on the same straight line. So that means that moment is 0 and resultant is also 0 fully. Okay. So this is whether you use this or this or this, where you locate points ABC and how you take your X prime is all your convenience, and how many problems you do and how to eliminate it. See, essentially is what? Essentially, you have 3 equations, okay? And you can solve for 3 unknowns. So either for 3 unknown force components, if you want to do that, do this, fine enough. But on the other hand, if you make sure that by doing this, say by taking the moment about A, a proposition, so then the force which is acting at A can be eliminated, right? So if you take this one, if you take MA, MB 0, and if you take Fx prime, so if there is any force at A can be eliminated, any force at B can be eliminated from that equation, and you can come up with a simpler set of equations, or even this, okay? So it's a matter of your convenience. We just leave it to you. So you, by doing a number of problems, you will get these ideas one by one. So you say that, okay, I'll use this or this or this or any direction. This X prime here is also arbitrary. You can take any convenient direction. If the unknown force is, for example, in a certain direction, X prime. So if you want to eliminate that, you take the component Y prime direction and set up the equation. Okay. So like this, please go through this concepts. You are familiar, you have been using it, but we want to go in deep, want to understand the philosophy of all these set of equations. Otherwise, if you have a statics problem, they simply say, okay, a sigma f is 0 and moment about any point is 0. But what is the basis of that? They will not explain. So, okay, we try to understand what is the basis. And then, of course, I borrowed the equations from dynamics, but sometimes I keep jumping back and forth. We will do that. Okay, please try to understand the book on Merriam or Hibbeler or anything, and please go through it. All right, I think if you have any questions, good. I mean, I'm getting some good feedback from you now and then. That's nice. Keep doing it. I like it. Okay, I think I'll stop here.